Hello, welcome back to Math 332 Linear Algebra. This is a video for sections 2.2, where we're going to look at how we can actually compute the determinant of a matrix by using row reductions. And this is also one of the videos where we're going to talk about the various property of determinants. So in the first video, we basically just use the definitions in order to compute the determinant of a matrix. But now we are going to explore various different properties for determinants. And the main things in this video is going to show you actually we can also compute the determinant of a matrix by performing row reductions. And let's get right to it. All right, let's begin by looking at the objective for this section. So at the end of this video, you should know some of the properties for determinants, and you should know how to compute the determinant of a matrix by row reductions. All right, let's look at the properties for the determinants. And if you remember from the previous videos that when we do cofactor expansion, we can do cofactor expansions along any rows of a matrix and also along any columns of a matrix. So everything that we mentioned here, even though we say that rows and the results will be still the same if you do it on the columns, okay? So remember that the determinant of A is equal to determinant of A transpose. So every property that we mentioned in this video that is true for the rows will also be true for the columns. Okay, so instead of keep saying that rows and columns, we're just going to keep concentrating and just say row, but with the understanding that the same property will still apply when you talk about columns, okay? So now this first property says that if you have a square matrix, which is a matrix A, is n by n square matrix. So suppose you perform an elementary row operations to get to this matrix B, and the elementary row operation is, let's say you interchange the first row and the second row of this matrix A. So you compute the determinant of this matrix B and you compute the determinants of this matrix A. The question is, what is the relationship between the determinant of A and the determinant of B? And this property says that they are actually differ by a negative sign. So the negative determinant of B is negative determinant of A. So that's what it says. And you can see this is an example of a 3 by 3 matrix. So you see that if you interchange the first row and the second row of this matrix, you get to this. So the determinant, okay, for this matrix and the determinant for this matrix is differ by a negative sign. Okay, so one of the consequences of this property is that if you have two rows, and again, as I said, everything still applies for the columns. So if you have two rows of a matrix A, which are identical. So let's say your matrix A looks like this, and you can see that this row, first row, and the third row of this matrix is the same. Then immediately you can see that the determinant of this matrix is 0. All right, so how is this a consequence of the properties of this matrix, the properties of this determinant, okay? The reason is very simple. So you look at this matrix A. So this is a matrix A, right? The matrix, not the determinant. All right, so this matrix A here has the first row and the third row identical to each other. So imagine that you interchange these two rows. So you interchange them. So you interchange these two rows to get to the new matrix B. But because this row here and this row here is actually the same, so after you interchange them, this B is actually still A. They are still the matrix A because they are still the same thing. But if you compute the determinant, so if you compute a determinant, so we know from the properties that the determinants will be differ by a negative sign. So you will have determinant of A equals to determinant of B with a negative sign, but the B here is the matrix you obtain after interchanging the first row and the third row. So this one here is still A. So when you have determinant of A equals to negative determinant of A, you can move this across the equality sign, and you will have 2 determinant of A equal to 0. So you will have determinant of A equals to 0. In general, if you have a number alpha equals to negative alpha, then this number here has to be 0 because any non-zero numbers would not satisfy these equations. So that is one of the consequences of this first property of the determinants of a square matrix, okay? So now, if you look at this particular example here, you can see that because this row right here and this row right here, they are identical. So immediately you would know that the determinant for this matrix is 0. Okay, so now let's move on to the second property for the determinant. So what it says is that if you have a square matrix N, let's give you an example here, which is 3 by 3. So you have a square matrix A, and you have another square matrix B. A and B are almost identically similar to each other, except that right here, this first row right here of the matrix B is actually K times the first row of matrix A. Right, so everything else is the same. You can see that all this is the same, but one of the row is a multiple of another row, okay? Right, so now if you compute the determinant of this matrix and you compute the determinants of this matrix, again, what is the relationship between these two determinants? And the answers is that determinant of B is actually K times determinant of A. So if you look at the way we write determinant using these different notations, you can kind of see that the determinant for this matrix is the same as K times the determinant of this matrix. And kind of like you can do factorizations, but for one row, you can do one row factorizations. Again, this is also true for the columns. So you can do one column factorization of one row factorizations. And the reason is very simple. Because if you remember the cofactor expansion, so if we do, say we do a cofactor expansions on this matrix, so let's get rid of this. So let's do a cofactor expansion for this matrix B. So the determinant of matrix B, let's do the cofactor expansion along the first row. So you have KA11C11 plus KA12C12, and then plus KA13C13, and obviously we can take out the K. So you have A11C11 plus A12C12, and then A13C13. And this, right, A11, okay, A12, C12, A13, C13. So this right here is precisely the cofactor expansions for the matrix A. So you have determinant of B is equal to K times the determinant of A. And you can see cofactor expansions that you perform is along a particular row. So this is, if you look at this part right here, the consequence of it is like you can factor out the constant K if your constant K is in a single row. Okay, so that explains why we have this particular property here. Okay, let me give you a quick example. So let's say right here, this matrix right here, okay, so you can see that this matrix right here, this row right here is 1, 2, 3, 4. This row right here is actually 2 times this row. Second row is actually 2 times the first row, right? So you can see if you multiply 2, 2, 2, 2, you get the second row. And because of that, the determinants of this matrix is 0. How do you know that? So we are going to apply property 1 and property 2 together. So let's compute the determinant of 1, 2, 3, 4. Okay, 2, 4, 6, 8, and then 1, 2, 3, 4. All right, and then you have, oh, you already have a 1, 2, 3, 4. This is not so good, because if you see this, you already immediately see that this determinant here has to be 0, because you have 2 identical rows. So this is my bad. Can I change this to anything but 1, 2, 3, 4? Let's change this to 4, 5, 6, 7. All right. Okay. Sorry about that. So this new matrix, okay, so this new matrix A, the determinant is still 0, okay? So if it is not, if I didn't change it, the determinant is obviously 0 from the first property. We don't even have to use anything about the second property. But now I want to use that. So this right here, you can see 1, 2, 3, 4. If you compute the determinant, let me use this notation so that you can have another example with different notations. So you have 2, 4, 6, 8, all right? And then you have 4, 5, 6, 7, and then you have 5, 6, 7, 8. So I am factoring out the factor 2 in the second row. So I'm taking it out. So that's determinant of 1, 2, 3, 4. Then this will be 1, 2, 3, 4. Okay, and then the rest is the same. I'm factorizing it only on a specific row. In this case, we are factorizing it on the second row. So now we'll see that the first row and the second row, if you concentrate just right here, you see that the first row and the second row here is the same. So by the first property, the consequence of the first property, we know that the determinant here is 0. So 2 times 0 is 0. So we know that this determinant here is 0. Okay. And this gives us the corollary, which basically says that if you have 2 rows or 2 columns of a matrix A, if they are multiple of each other, then the determinant of A is equal to 0. So this is slightly different from the one that we have here. So this one says that the 2 rows or the 2 column has to be identical, then the determinant of A has to be 0. But coupled with this new property, we don't really need them to be identical. We just need 2 rows or the 2 columns of a matrix A. If they are multiple of each other, that will also guarantee that that determinant of that matrix will be 0. Okay, so I'm going to ask you a question, which is right here. So suppose you have a matrix A, and the determinants of this matrix A is alpha. Let's say that's alpha. And if you multiply that matrix Ka, so Ka by the scalar multiplications of a matrix, this is going to multiply every entries in A by K. So you have a square matrix, all right? So A is a square matrix. A is a square matrix, all right? A is a square matrix. You multiply it with a scalar, which is a number, Ka. And the question is, what is the determinant of Ka? Ka is not a 0. So what is the determinant of Ka knowing that determinant of A is alpha? I'm going to give you a moment to work on these problems. Then I will come back and we can look at the solution together. All right, welcome back. And I hope you know that the information that I gave you is insufficient to answer these questions. Because I didn't tell you what is the size of this matrix A. I just say that A is a square matrix, and you will see, if you think deeply, you will see that the determinant of Ka will depends on the size of the matrix. So let's say here your A is 3 by 3, okay? So your Ka here, if you compute the determinant, I hope you will see that the determinant of your Ka, right? I hope you will see that your determinant of Ka is not, okay? So it's not, this is not true. It's not K times determinant of A, okay? You cannot factor out the K like this because the so-called factorizations property that we have from before is only true for one particular row or one particular column. So if you have A as a 3 by 3 matrix, for example, so you will have your A11, okay, so you have your A11, A12, A13, A21, A22, A23, and A31, A32, A33. If you multiply K to this matrix, you will have to multiply everything with a K. And then if you are going to compute the determinant for this, then you will have to use the properties that we talked about before by factoring out one by one. So you have a K, all right, and then determinants of the A11, A12, A13, but you still have the K, A21, and all that thing here. So they still have a K, they still have a K, they still have a K, because when you do factorizations, you can only do factorization one row at a time. So you take one of the K out, and then you have to factor the K from the second row, and then you have to factor the K from the third row. So you can see if your matrix is of size 3 by 3, the determinant of Ka will turns out to be K to the power of 3 determinant of A. All right, so in general, this is not true. So if I can show you an example to see that this is not true, okay, determinant of 3 times the identity matrix is not 3 times the identity matrix, but is 3 to the power of 3 times the determinant of the identity matrix. So what we have here is that if your A is a square matrix of size n by n and K is a non-zero scalar, then the determinant of Ka is K to the power of n times determinant of A. So I hope you get that answers, okay? So I also hope that I purposely left out the information so that I want you to kind of see whether or not you will notice that the answers actually depends on the size of that matrix. So factorizations, this property here, the factorizations that we mentioned right here is true one row at a time and one column at a time, because when you do a cofactor expansion, you do it one row at a time and one column at a time. So when you have a k on that particular row or columns, you can do factorization like that. But when you have k multiplier matrix, that is every element in A will have to be multiplied with that scalar k. So situations is different. So you have that, and factorization row by row or column by column will give you this kind of result. So this theorem right here says that if your A is a square matrix of size n by n, then the determinant of Ka will be k to the power of n times determinant of A. All right, so let's look at the another property for determinant. That is, again, your A is a size n by n matrix, and if you do a legit row operations, in this case, let's say, for example, you are taking the first row of the matrix, and what you do is you change it to k times the second row of this matrix, okay? All right, to get to this matrix B. So matrix B is obtained after you do this particular row reductions on this matrix A. All right, so you take a matrix A and then you do this row reductions. Okay, let me write it here so that this is similar to the standard notation that we usually use. So we are changing the first row of the matrix A, and we do that by taking it plus k times the second row of the matrix A. All right, so we compute the determinant of A and we compute the determinant of B, and the question is, what is the relationship between determinant of A and determinant of B? Then the answer is that they are the same. Okay, so when you do a row operations like this, okay, to get to this matrix B, then the determinant of this matrix B and the determinant of this matrix A, they are actually the same. Okay, why is that so? All right, so let's take a look at the reason why it is true. But before we do that, let us just remind you that, again, when you compute the determinant of this matrix, it is the same as you compute the determinant of this matrix. Okay, so you take a look at this. So it's kind of like you split this matrix. So you have A11, A12, A13. So you split it right here. You basically take something that looks like this. Okay, and compute the determinants, and you take something that looks like this and compute the determinant. Okay, and you get that. You can kind of like split this to this particular determinants that you want to compute into these two parts. And so this is not saying, though, this is very important. This is not saying that determinant of A plus B is equals to determinant of A plus determinant of B. This is not true, okay? So this is not true. We are not saying that. We just say that everything else is the same, and then the first part here is written as a sum of kind of like your A11 matrix and the B11 matrix, A12, B12, A13, B13, and you can split it into this, okay? And why is that so? This is, again, easy to see if you remember the cofactor expansions. So let's say I want to compute the determinant of this matrix. So I do my cofactor expansion along this row. So what you get will be this terms right here, right, with the cofactor C11. This terms right here with the cofactor, this term right here with the cofactor, and obviously we can multiply and regroup. So we multiply and regroup. We have this. We have this, and this is exactly the determinant of this matrix, and this one right here is exactly the determinant of this matrix. Okay, so now we know that if you have a determinant of this matrix, that determinant can be computed by splitting it into these two. So this will give you the sum of these two. Okay. Now, so if you have a determinant that looks like this, okay, so this is A, right? And then you do row operation. In this case is R1 plus K times R2 to get to B, right? So this is determinant of B. So this one right here is determinant of B. All right, so this one right here is determinant of B. So take a look at this part right here as the remark that we have before. We can split them into these two parts, right? So everything is the same. All these terms here, these are the same, all right? These are the same. And then here you have the A11, okay? Here you have the A12, here you have the A13, and then here you have the KA2, here you have this, and then here you have this, all right? So that's that. And then, okay, so we successfully split it into two by using the expansion along cofactor expansions with the first row right here. Okay, now from the properties that we have before, we can factor out the k because this k is only multiplied on the first row, so you can take the k out. Okay, so this is okay. This taking the k out is okay. And do you see that by taking the k out, you have these two rows identical to each other? So these two rows are identical to each other. So therefore, the determinant for this is 0. So you get back to this one. So this one here is just 0. Actually, this is also 0. So therefore, you will immediately see that this is nothing but determinant of A. So the determinant of B is actually the same as determinant of A. So if you do a row operation like that, the determinant will not change, right? So the determinant of A and the determinant of B will be the same. Okay, so this is another properties for determinants, which is pretty cool. Okay, so once you get all that, let's look at this questions. Let's practice a little bit before we move on to the final steps, which is how to compute determinant using row reductions. So I want you to take a look at these questions and we'll be back. All right, I will give you a couple of minutes to work on the problems and you can pause the video, and when you are ready, you can restart the video and I will come back and we can look at the solution together. All right, welcome back. So you are given the determinant of this matrix here is beta. The question is, what is the determinant for this matrix? Okay, so this is not too complicated. So you have 3, 3, 3. Okay, we can factor out the 3 one time, one row at a time. We have the pi, pi, and pi. We can also factor it out one row at a time. And then we have 6, 6, 6. We can also factor it out one row at a time. So it's taking the 3 out and taking the pi out and taking the 6 out. So it turns out that you just have to compute the determinant of this. All right, so you have negative. So you have 18 pi right here. Okay, and then we don't have this information. We do not have the one that is G, H, I, D, E, F, A, B, C. What we have is this one, but you can see they are the same if you interchange the first row and the third row. So if you interchange the first row and the third row, the determinants will now differ by a negative sign, and then this one right here is exactly that we have from before, so that is beta. So the answer will be negative 18 pi beta. So I hope you get this answer right. Okay, this is nothing but utilizing the properties for determinant. Okay, so let's look at another problem right here. So again, you are given that's the determinant. Okay, so the determinant of this matrix here is alpha. So this is the determinant. So the determinant of this matrix here is alpha. The question is, what is the determinant for this matrix then? Okay, so take a look and we'll be back. All right, I am going to give you a moment to work on these problems, and you can pause the video. And when you are ready, you can restart the video and I will be there to discuss the problem with you and work on it together. All right, welcome back. And let's review the answers, the solution for this problem. So again, this is the determinant of this matrix is given as alpha. The question is, what is the determinants for this matrix? And as you can see, that is a 3. So we can factor out the 3. We can factor one row at a time. So after you factor it out, the 3, you will see that this determinant right here, is exactly the same as this determinant. Why is that the case? Because this determinant right here, so this matrix, so if you forget about the determinants, just concentrate on this matrix. So this matrix here and this matrix here, what is the relationship between these two matrices? So let's say we call this matrix A, we call this matrix B. You realize that A, if you do these row operations, which is take the third row, and then you take the third row plus K times the first row, you will get to this matrix B. So if you call this matrix A, and if you do these row operations, changing the third row of this matrix A, so if you are changing the third row of this matrix A by taking the third row plus K times the first row. So this is the first row, you K times of it, you have KA, KB, KC, and you get to this matrix B. So this is matrix B, and this is matrix A. So this is B, and this is A. And because B is obtained by doing these row operations to B, the property says that that two determinants is actually going to be the same. So that's determinant right here. That determinant right here is the same as this determinant, and we know that this determinant is given by alpha. So your answers will be 3 alpha. So I hope you get this right also, okay? It's not very complicated, and that's how you are utilizing the properties for determinants to figure it out what is the determinant for this particular matrix, okay? All right, so let's move on. And the final things that we want to talk about is how do you actually utilizing all that properties that we talk about to do to compute the determinant of a matrix by doing row operations. Okay, so suppose you have this matrix A, and we want to compute the determinants of this matrix not using the cofactor expansions but using row reductions. Okay, so let's take a look. So first of all, I would like to interchange. This is just, for example, you don't really have to do it this way, okay? But, so for example, I would like to interchange the first row and the second row of the matrix. So I would, if you interchange the first row and the second row of this matrix, you will introduce a negative sign. So that's the property. So I have that. And 6 and negative 12 and 18, they're all multiple of 6. So I'm factoring out the 6. So I factoring out the 6, okay, one row at a time. So I factor out the 6 on this first row. I have 1, negative 2, and 3. So that's what I have. I have negative 6 right here. And then I'm doing row operation to kill off this number. So how do I do the row operations? I will be changing my third row, and I'm taking third row minus 2 times the first row. So that is how I get rid of this. And remember that when you do row operation like this, it will not change the determinant. So this determinant right here and this determinant right here is still the same, all right, because I'm just doing row reduction of this type. And then when this is dead, I am going to kill off this number. So right here, I'm going to do another row operations where I'm going to take the third row minus 10 times the second row. So I'm changing that to get to this. And again, doing row operation like that would not affect the determinants. So as you can see, those determinants are still the same. These determinants are still the same. And when I get to here, I don't really have to do any row operation anymore because this is the upper triangular matrix. So when you have upper triangular matrix from the first video, you know that the determinant is nothing but the products of the diagonal. So now you have negative 6, multiply 1, multiply 1, multiply negative 55, and you will get the answers as 330. So this is one example where you can compute the determinant of a matrix using row operations. And you can see the objective of performing the row operations is to reduce it to something that is upper or lower triangular matrix or even diagonal matrix, and we can use the property that we have from the first videos. Once you have a upper triangular matrix or lower triangular matrix or diagonal matrix, the determinant is nothing but the products of this diagonal. And this concludes our discussions for this particular sections. All right, this concludes our discussions on sections 2.2, and in the next video we are going to look at sections 2.3, where we're going to explore some other further properties for determinants. And in particular, we are going to look at the main reason why we study determinants. That is, we're going to use determinants to completely characterize when a square matrix is invertible. So we're going to look at that particular theorem in the next video, and we are also going to look at the proof of that theorem. And so things is going to be a little bit theoretical. Okay, so I will see you then.